Next slide. Okay. So yesterday, I think we were discussing about the potential of the galaxy, and to determine the potential, they said that you need to have the light distribution first calculated observationally. Once you calculate the light distribution, then one can have the mass to light ratio multiplied by that, you calculate surface density, surface mass density, and then you calculate the volume density by the projection technique. Then you can solve the first equation to get the projection. Once you have the potential of the galaxy, let's say all this can be done, then one can write a Hamiltonian for this and solve an equation of motion for a given star. So that's the idea to go forward in that direction. So because of the short of time, in 1 hour, I will not be able to complete many things. So if you have questions, so you can. So what we decided is that the galaxy, we consider only the axis symmetric part, the high independent part. Clear, everyone? No spiral arm in that. No non-axis symmetry. Wherever there is a high dependence, we are not ignoring that. So your potential is in cylindrical coordinate for this galaxy. It will be only function of R and Z. We are considering this galaxy in which supposedly this is a plane and this is the z-axis and it's the plane of the galaxy. Stars are all moving. So because of the phi independence, as we said, we could write down the Hamiltonian for this and consider the unit mass of the star, so you don't care about the 2m part. So it's basically e square by 2. So you have the radial component, right? And then I was asking yesterday what would be the next term here. So it should be e square by anyone? R square plus z square plus 5 function of r. What is the radial equation of motion? PR dot equals to minus del h by del r. Right? What will be? Minus what's the term? The derivative is the right hand minus 2 by r cube. Then it is one part, right? Positive or negative? The negative sign here. Positive. So this is equals to 3 pi square by r cube minus is this correct? What about the peak height? No. So P5 dot is equals to 0. So P5 is a constant of motion. Okay? And pz minus del x by z, right, equals to minus 2 pi by del, right? Like this. Okay. It should be the derivative only here, no half. So please check this. Okay. So we can solve this equation from we go forward. So we have only the meridional plane in the galaxy that is of the stars. This we don't have the phi is only constant. Right? Now we have only equation the radial direction and in the vertical direction. It's all in the radial direction or in the vertical direction. Right? So if you like, we could go to the R double dot here, like that terminology. So we can go substitute PR equals to R dot, so it's R double dot, right? And then one can write this in terms of some kind of effective potential. Into that. So because P phi is like an LZ, so it's LZ square by 2 R cube, right? Z square R cube. So one can write Z double dot. The two equations from here. R double dot minus del phi effective by del R and double dot minus del phi effective by these two equations. We have phi effective equals to phi plus, we will say this term is coming from here. Substitute P phi is LZ. So what's the term here? Effective potential. We have all done it before. Huh? LZ square by N is unity here. Right? So this is effective potential. So essentially, what we learn is that the star in an axisymmetric potential conserves the angular momentum as it goes around the galaxy. So the vertical component of the angular momentum, the z component of the angular momentum, and it basically have motion in the radial direction and in the direction. Okay. Now, what from here to go forward from here, you need this some form of a potential, right? Some function, something analytic, numerical, anything that you need to supply, which you're supposed to calculate from all the way that we discussed this, right? So without that, we cannot move forward. Okay. Now, that is the trouble because you do not know what is the potential to consider because there are many different kind of potential. One I will consider, of course, from some argument from the observation. So, but before that, you can think about something like when you look at a galaxy, like the disk-like galaxy, right? Let's say what is the properties of the galaxy? It's like a big spiral galaxy. Here you seeing it in edge on. Okay? The thickness of this galaxy in this direction are much smaller than the size. That's why it's selective. Which means that any radius z divided by r is less than 1. Okay, so it's effectively a two-dimensional plane. Not exactly, but two-dimensional plane. But with a little bit of vertical stratification, which I just discussed. That's the structure of a spiral galaxy that we are considering. But you can think about it effectively, it's just a 2D plane also. In this 2D plane, we understand that there are two different motion in two different directions. Yes, equation of motion in the radial and the vertical, and while it goes around the galaxy, it's conserving the angular momentum z component there. Now, having said that, one can think about now such like a disk of stars. Okay, if you think of the disk of stars, would you think that the stars would go around like anything, or it can go like this, or it can go like this? What kind of orbits do you think the most likely assumption that you want to have? Elliptical, all elliptical. So if I have almost like a circle, right, in a projection, as I said, there is a thickness here, but you said that okay, we'll make some kind of elliptical, right? So we can go to this approximation. So which will be, let's say, we can think about that at a given radius r, guiding center radius, or you can say r naught. Is considered that the star with good approximation is a circular orbit. Why circular orbit? At a given radius r naught, it will have an angular momentum Lz. Okay, and at a given angular momentum, the minimum energy of the circular orbit. You can minimize the potential, we will get the condition for a circular. Clear? Anybody? What did I say? I said that at a given radius, you have a fixed angular momentum energy. Move to another radius with a different angular momentum. So this angular momentum Lz is for a given star. A given star that is going around the galaxy. Okay, given star that is going around the galaxy. For a given angular momentum, you can think about that the star would settle on an orbit which probably the minimum energy. Okay, so calculate the energy of a particle. So E equals to the kinetic energy plus the potential energy, say effective potential energy, and you can minimize the energy, and you say you find a condition that is basically a circular centrifugal force versus the gravity. Okay, so it's not very difficult, but we say that there is a circular orbit. We have n number of circular orbit arranged constantly. So that's what probably would give an impression of a disk. Imagine. So you can populate this part like so densely that you can think about the each stars going around in a circular orbit, and that's how the disk is formed. That's a basic model. That's a basic model to start with. Basic model start. So then we say that at r naught, at a given radius r naught, there is a circular orbit. Okay. Fine. Now what do we do? So in a circular orbit, what we want to do is that we want to know what kind of motion this particle will have, or the star will have. So we say that from r naught, give a push to the star to in a radial direction. Okay, so you consider a radius like r, okay, and a small displacement. Fine. So you push the star in the radial direction. So we have x equals to r minus r naught. Fine. This is the quantity which is ideally giving a small displacement. Right? At this radius r naught, we have a effective potential which would vary with radius. And correct. So what can you do here? We formulate this equation of motion in terms of a equation of motion of a small displacement along the circular. What is the assumption? Assumption is that all the stars in the galaxy, or in this model of a galaxy, rather moving on a circular orbit to start with. And then you say that at any, this is can do at any radius. Fine. So then we have an effective potential at r naught and z, right? Z0, right? Plus, what can we do? We do the Taylor expansion of the potential around the circular orbit. Around the circular orbit. Can you do the Taylor expansion now? What's the term here? Be louder. You're saying. Del phi by del R. You mean effective by del R? To x plus del phi by del. What is the here? What about the okay? You can do it in. So this is a 2D, right? So similarly, I forgot to say that you can think also that you give the push star in vertical by some z, and in the plane of a galaxy that z equals to 0. Z equals to 0 is where the plane of the galaxy. Okay, so you can think about z not is actually 0. So then into z, right? Plus half into x squared, right? Or like this, fine. So there will be terms of the higher order and there will be mixed terms. Is it clear? There will be also mixed terms. Okay. So then we can think about that R double dot is nothing but x double dot, correct? Equals to minus. We can call this term. Let's define a term here. So let's call it kappa square. Is a definition only. Calculated at equals to 0 and R naught. And then we have another term, mu square is a definition again. At z equals to 0 and R naught. Fine. So we can now think, if you like that, then you are basically your R dot equation, your R dot is basically going to be x double dot minus kappa square. Correct? And clear? This one? This. I call this del to phi effective del R2 as kappa square. So the half kappa square into x square. So the R dot is basically x double dot. So you can make a derivative here. It's a, don't you see? Suppose I wrote this potential expansion. This is the term which is for the circular orbit. Right? This will be satisfied circular orbit. Now I have expanded this. These are the bodily force terms, so the stars are not moving. Right? So they are basically bound in a circular orbit, right? This will give a force term which will make the stars go around, right? Which is not the case. So if we don't look at that, then you have the second order term here, which is basically frequency square, some kind of frequency. Okay. So the kappa square, is it clear to everyone? Any question? Yes, go ahead. Huh? Where? From here? Can you be louder, please?
Half of the square in a 550 R square is 100 square.
This term this is the first of all, this part is clear Taylor expansion. This is the zeroth order, the first order, the second order. Right? I stop at second order. You could go up to like higher order. Don't get. Now then I define this second derivative of the effective potential as a definition, as like a capacitor. I call it a capacitor. You could write down exactly here del to phi effective del R square into xx. So what I do here is that R double dot is nothing but R double dot is x double dot. Right? So the x double dot, and then you make a derivative with this, but this term is calculated at R is equal to R naught into at Z naught. This is also the same. This is at R equals to R naught and Z naught. Okay, all these terms are calculated at the location of the circular orbit. Okay. And then I define two different terms here. The second derivative term is a definition. And when I look at that definition, I see I have an equation of motion which is very simple. Is it clear? So x double dot and z double dot is nothing but this looks like a very simple harmonic motion. In the radial direction about the circular orbit, it's doing just a simple harmonic motion. Like this. And in the vertical direction also is doing simple harmonic motion. Approximation is the displacement should be small. This is small angle or small displacement approach, small oscillation problem, right? So you cannot think about like stars moving very far off the plane and you say, okay, this would be very low. It's only for a small approach. But what it brings to you is a very interesting part here. Is that what we learn in this is that x double dot is doing a simple harmonic motion in the radial direction, and in the vertical direction is also doing a simple harmonic motion but with a different frequency, and these are different frequencies. These two frequencies are basically called the epicyclic frequency. Okay? Epicyclic frequency. Epicyclic frequency of a star. Okay, running late. Now, what we make out of this? So what? So what we get out of the? We wanted to know the orbit, right? So the orbit is so in this potential. What we learn is that now I can go back for you to do this term. Suppose your phi, the potential of the galaxy, which you not know. But suppose I give you a form, you can estimate the frequencies. Very easy. So suppose it's basically nothing but Gm by R. Okay, the potential. You are familiar with this potential? What is it? Huh? What? Gravitational potential. Gm over R. Do you know any system where it will be applied? Can be applied? Center. Huh? You have a center. Central mass. You have a central mass. Do you know anything where there is a central mass and sun, Earth orbit? Right? There is the mass of the sun and the radius at a given distance. So given this potential, you can estimate what is the frequency kappa square, mu square, and also the angular momentum. Right? It's doable because it's a very simple thing. Right? Any question on that? Then you can have a potential which is, let's say, phi equals to half into, let's say, A into R square, the harmonic oscillator potential, right? Harmonic oscillator potential. You can also think about calculating these frequencies. It turns out that whenever this is also called as the Kepler potential, Kepler's potential. In a Kepler problem, which is governed by the gravitational potential of the sun only, okay, in which the star or the planets moves as a test particle. Okay, planet moves as a test particle. Okay, in that these frequencies kappa, mu, and there will be a frequency of the circular motion also, because you have a Lz is an angular moment. You know the velocity, and then at a given radius, you know what is the Lz, then you can estimate the circular frequency. Correct? Can do that. So you will have also a circular frequency. It turns out that we call that circular frequency the omega. Okay. In a Kepler potential, this all say you can take as a task to derive. Very simple. Okay. In a Kepler potential, therefore, if you estimate this using this term, they will be all same. And if you do in any other potential, they will be different. In terms of particularly when you have a potential of a galaxy, in which neither it is a Kepler problem, nor it is something to do with the harmonic oscillator potential. So this is all in those cases, kappa and omega and mu, they are not same. In general, for a given potential, omega is not equals to kappa, it's not equals to. Why I am telling all this? First of all, that when you look at if you are given a potential, okay, which is very basic for you to understand the dynamics. In that potential, the first thing to calculate is the frequencies. If you let a star or a particle go around that, so it will move in this some orbit, so you need to know the frequency. Okay, so that's the first thing to learn about a dynamical system or the dynamics of the system. The frequencies. What are the frequencies? What are the vibrational, rotational, anything that you want to know? The frequencies of it. And it turns out that in a Kepler potential, the planet actually goes in a plane, right, which is the perpendicular to the angular momentum axis, and in that it's such a way that it goes around and it comes back at the location. And this is, for example, let's say you kick a star from this direction in this potential, you go around, and it comes back exactly at the same location. Why? Because all the frequencies are same. All the frequencies. But if we do this here, let's say we kick a star here, it goes around, and because the radial oscillation is there, so they may not come at the same location. They may not come at the same location. So go around, and then go around. Continuing going. You follow? This is because the frequencies are we are going around in this around the circle with the frequencies is omega, because this is what we assume, because it's a circular orbit, right? But because now we know there is a oscillation frequency in the radial direction, then it will not be coming to the same location. It will go to different location and it can continue. So this is a with a thickness, and it basically fills up a space. It's almost like a tube. So in the general galactic potential, a star would not be, the orbit is not closed. The, the, the implication of this is that orbit is not closed. Orbit is not closed because the frequencies are different. Okay, so now it is exactly similar to something like you have learned, like probably Lisa's figure. What is that? Basically, it's a harmonic oscillator in 2D. There is one direction in the x, there is one direction in y. Now, so these frequencies can have different different values, but then they also have ratios which are can be different. So if the ratio of this is a commensurate number, or it's basically, let's say, kappa over omega is integer, ratio is an integer, then this orbit may close. For example, you can start, like, for example, center here, you can maybe close, like after one turn, like now there will be like this. So there will be different combinations of this. But if this is not integer, if this is not an integer, then this orbit will not be closed. It will be like this. This is called a loop orbit also. It's called a loop orbit. For our sun, for example, so we can go into this, that there will be, for example, at every time a star goes around this, will go around this, and they will come. But then if the two frequencies have an integer ratio, then the orbit will be closed after, like, so many times. So 2 turns, 3 turns, depending on what is the number, right side. Okay. For our sun, kappa over omega is 1.3. This we can estimate actually. This you can estimate for our sun. And the measured number is such that kappa over omega is 1.3, and the orbit of the sun around the galaxy are like this. Do you understand this? Clear? So orbit of the sun around the Milky Way galaxy is not on a closed orbit or not on a periodic orbit. It does not go around the same location and come back. But it is a bounded. You can see like this thickness around this. You can see this, right? So I think I have some example. This is an example of a loop orbit. You can start with any. This is a very simple task you can actually do in simple Python program. You can do this, and you see at the end you almost seems like a three-dimensional tube. It's like a toroid. Okay, so this is called an orbital toroid also. Okay, and in an orbital toroid you can see that there is a thickness associated with it. Where does this thickness come from? Everything comes here. This is where the details come into picture. Unfortunately, we cannot go. But if you think about what is this thickness? Why it is not thin? Why it is not this thick? Right? What determines that? What determines that? Huh? Which ratio? No, it's not the ratio. The omega is basically a circle. It's a closed circle. What determines in this is the energy of this motion. So associated to that, there will be an energy associated. So it's basically half h dot square plus kappa square into x square, right? And this is a conserved quantity, isn't it? This is a conserved quantity. That's the beauty of this. Since this is a conserved quantity, every time you have a frequency fixed, you have that the thickness of the toroid, like, will tell you how much the orbital spread. For example, if a sun is here and it goes around this, and if it is too much, it may go too far away. Okay, so that's the understanding that we have. We follow. So thickness is determined by the radial epicyclic energy, and which is a conserved quantity. Okay. For a planet, this does not happen. It's a closed periodic orbit. Everyone goes in a periodic orbit, so there is not much like this. This is basically there is no motion around this radial motion. Through an approximation, which is governed by the Kepler potential. You change this, things might change, and that's where the research goes. Okay, so that's the logic or all behind this. Now you can think that when we started with saying that the galaxy is made up of like m stars all going in a circular orbit. Now we can replace the circular orbit with a loop orbit. N number of loop orbit to be is like a bricks. It's like a brick which you can place into this and you can make galaxies. Simple spherical, two-dimensional galaxies, right? So that's this. You can use this as a brick. So these orbits, when we calculate these orbits, you want to know what is the fundamental building blocks. What is it made up of? It's like a skeleton. You can put skeleton on that, and you can put stars later on. That's how it works. Okay. So that's how we orbital the dynamics becomes very very important, and you can see that this loop orbits have as is written here has a sense of circulation, so it goes around the center. Okay. Now, with that, I think I want to move ahead and go do something slightly different. There is one part left, which is basically the center of the galaxy. What happens at the center of the galaxy? Without knowing much about the, so this is what we did. Even we don't know the potential. You see that? Even if we did not know the exact nature of the potential. But is it any given potential? If we can do this, then this works. Now, if we can think about, say, a little bit of digression to this, but I'll come back the center of the galaxy. You have learned about the rotation velocity of gas in a galaxy. Have someone talked about the rotation curve of a galaxy? No, yes? Isn't it? Who thought? Rotation curve.
We were talking about that.
Yes, yes, yes.
So that it was briefly discussed.
Briefly discussed. So just keep hold on to this because I need a bit of an introduction to come back to that state. So what how do we go? See, so far what we talked about is basically about stars, right? Stars in the galaxy. Galaxies actually, most local galaxies are made from stars. 90% of the constituents are basically coming from the stars of the baryon. The galaxy has mostly bariums, and then you have also the dark matter. If you do not know, it's an hypothesis, right? Then we can think about that if we take any local galaxy, not a very high redshift one, where we do not know all this measurement very well, but for a local galaxy, 90% of the baryonic mass into stars. About 10% is in the gas. About 10% is in the gas. This is a typical galaxy like Milky Way galaxy. You deviate from the Milky Way galaxy, there can be this. So this is where it's come. So M gas, mass of the gas. The gas is basically coming from neutral hydrogen gas, and then you have molecular hydrogen gas, and then you have CO, all that. So you can do. So M gas divided by M star. This can be, this ratio can be or this ratio is not zero, okay, because most galaxies have actually gas there. Whether we measure or not measure is a different, because the stars are made from gas. Stars are made from gas clouds and they form stars, and the efficiency of forming stars is very low, few percent. So if giving like a mass of the gas like 100, then only few percent of the gas will be formed into stars. The rest will be left over. Okay, so it's a very inefficient star formation, very inefficient. Okay, so this fraction is not zero, it's non-zero, and it can be more than one also. So I do not know what numbers to write. So it's like greater than zero, but there is a limit on this. There can be a galaxy when most of the galaxy is basically gas. Only few stars just form. I'm talking about you can go all the way up to high redshift galaxies, right? But in local galaxy, this is for Milky Way like galaxy, it is less than one. Okay, if you have a low surface brightness galaxy, which is LSP galaxy, where this is generally gas dominated galaxy, this ratio can be of the order of 1 or more. Okay, so this ratio is like this itself is a study and itself is one can discuss this. Now, why I'm saying this, so in a galaxy like Milky Way, you have stars and you have gas. The gas mostly, predominantly, it is the neutral hydrogen gas. So of the gas, you can think about even most of them are actually in neutral hydrogen gas, not in molecular, not in, they are very little. Okay. Now this neutral hydrogen gas one can observe using the 21 centimeter emission, right? So and then one can calculate what is called the circular velocity curve as a function of radius for the galaxy, right? Which is the circular velocity. What is the circular velocity? Circular velocity of the neutral hydrogen gas. The gas that you see is not like that. It's not like a diffuse gas. The gas is like gas clouds. Neutral hydrogen gas, like probably they are in a big clouds, okay, and then they go around the galaxy. And why choose neutral hydrogen gas? Can anyone explain to me? Why choose neutral hydrogen gas? And we say, okay, we calculate circular velocity like this. These curves must have data points you must have seen, right? Like that, right? And they say that okay, circular velocity is like Newton feet, and it's almost like a constant, right? This is constant. So why choose neutral hydrogen? Why not stars?
Far outside the galaxy have the neutral hydrogen.
Far outside the galaxy,
Like,
right?
Where there are not as many stars to measure them.
So why choose that? Why not stars? We are interested in the galaxy. Why go far out the galaxy? No? Is this question clear? He said that we go far out the galaxy. Why go far out the galaxy?
Because you want to see the flat part where the dark matter.
You mean the dark matter is not here?
It is there, but the flat, the main thing is the
Why
flat.
worry about the flat?
Because then it should fall off, right? If there's no dark matter. If you want to see the fall off.
Otherwise, you see fall off. Okay? So that's why you look at that.
So you want to see outside.
The outside. But if I give you like say, okay, now if this was almost 40 years ago, okay, 40 years ago this is now we can measure stars which go even further here. Our capability has changed. Maybe easier to,
Determine with the
but I want to know why. What is the physics there? Why do we go for this?
data machine.
It's not easily. It's a lot of integration time. And it's not that easy. Um, any other comments, ideas? I don't have a lot of time. Any other ideas? Why don't we think? Why choose hydrogen gas?
Because the light.
So this is going to be present in the galaxy where stars might not have formed, and so you might not have enough stars to track all the way to the
The question is why think about go to the end? Why I can't stop here to determine the calculator? What is my aim? Is the aim to see this? The aim is to understand the potential of the galaxy. Don't forget that. Aim is to understand Dipanjan.
Similar is
Yeah, one, Bhaskara one. So aim is to understand the potential, measure the potential of the galaxy. Right? That's what we want to do. That's why we want to understand the motion of the object in that. Right? So if I say it is oh that's so easy, I don't know. So it's a very conceptual thing. Huh?
Stars and also most part of the stars
Yes.
are velocity of hydrogen. Velocity of stars.
No, there is a little difference here. You see, this is where it should come from. So it's what she's saying that if you measure the stars, what do you say? You measure the stars, you also measure velocity of the stars. The velocity of the stars and velocity of the gas similar.
Star, not similar, but also hydrogen is also hydrogen is the main element of stars.
Of the stars, yes.
If you measure hydrogen,
But it's not the same thing. The hydrogen that is in the star that are found stuck in the star. Hydrogen that we're talking about, they did not make stars. They're just the hydrogen gas clouds going around. Okay, so there are little important thing here we should understand this. If we think about a galaxy as a number of stars, okay, as I said, the most of the mass is locked in the stars. So 90% of this. A galaxy, when you think about an object here, so there are think about stars here. We want to understand the potential of this galaxy. Right? We want to understand the potential of this galaxy. How do we calculate the potential of this galaxy? Theoretically. So I have mass, mi, I have mass of the star, this is mj, right? So I can think about you are not in the right place, I suppose. Yes. It's a Maskarova.
Okay.
So the potential of the galaxy are basically so the galaxy exists on its own. It does not need another potential to be. Okay? Whatever the baryonic, non-baryonic, whatever you say, is the stars are basically like the motion of the star of this star is determined by the rest of the stars in the galaxy. So then the potential one can write simply sum over G mi mj potential energy is equal to Ri minus Rj. J equals to 1 to m, I not equals to j, right? Correct. So this is what it means. Is that what it meaning of this? This potential energy is a potential energy of the galaxy, which is made of any body, n bodies, n number of stars there. Each star, when it moves in the galaxy, it moves due to the n minus 1 stars. So the potential is not from anywhere outside. It's the potential due to its own gravity. So this is called a self-gravity. Self-gravity. Okay? It is not like self. Now, when you talk about the motion of the stars, suppose you say that, okay, I want to look at these stars, and this is where probably the center. So this star will be going around this orbit, so will be going around another orbit, like that. So any of these stars will be going around like in its own orbit. Once it does that, once a star moves in this orbit, the motion of this star is affecting the rest of the others. Okay? Through this potential, right? Because it's a long range potential. This is affected. What you need is basically is that what if we have a ballistic particle moving in the galaxy? Then that is almost like a test particle moving. It's a massless test particle. When a massless test particle moves in a galaxy, we consider I look at the motion, I immediately say, okay, we can determine the potential. Okay? Do you follow? So here we cannot take the stars and say determine the potential of all the potential because we need to know the motion of the whole, solve it properly. But if we have a ballistic particle which goes around this, and whose the mass of this do not affect the motion or the mass of this do not change the potential. Do you follow it? If a star moves, then this is the configuration. RIRJ is the configuration, right? RIRJ change, the potential configuration will change. Correct? If I have a ballistic particle, the test particle is a massless, they do not affect the system. So the H1 gas, 21 centimeter gas cloud, is like a ballistic particle. It's like a test particle movement. So that's why we take the hydrogen gas, neutral hydrogen gas, to estimate the circular velocity. Even better than the circular velocity. What could be even better if you want to find the potential which it moves? What could be even better than the balance gas, this hydrogen gas cloud? You want to determine potential and you want to disturb it, right? And I said that okay, if you do like the stars, then you have this trouble. Do you understand this? Yeah. So I said, okay, go to a test in which you say that consider a test particle which will not affect the potential of the gas. What could be even better? What?
Light.
Light?
Light.
Light. Photon, how can you can measure the velocity? How can I say that? We need to measure the velocity.
Lensing can be used to measure the dark matter.
Yes, but lensing does not use the dynamics, motion. Or no, the motion. Also, it depends on the lots of modeling and this that. So let me not get there. But I said like, what could be even better? Think about to go step back. Huh? What? H2 molecule.
Because the amount is much lesser than hydrogen gas. Each one is such. We will get something. It will affect the other mass.
Yes, but the only problem is that H2 molecules are generally not observable. You know why? Why you cannot observe molecular hydrogen? Why? Tell me.
Yeah.
No, not that reason. Does not have an emission. So why? No. You must ask about this. Every step there is a question. If you don't question, you will not know. Why molecular hydrogen is we cannot have an emission? What is the molecular hydrogen? Two hydrogen atoms stuck. And then we so it's because you need to this dipole moment is zero. Symmetric molecule. That's why you go to CO, which is non-symmetric. So you go there, so it's very interesting. So we want to know star formation. So the hydrogen gas collapse and form molecular gas, but we cannot observe molecular gas directly. So we look at CO and then infrared. It's a difficult problem. CO can observe because it's not symmetric. So the even better would be like I go from somewhere here and I come back, right? What is this called? You know? I take it to something even farther. Do you know anything like that? What could be? He said this is a stars, the hydrogen gas which is a bit farther. What could be even further and orbiting the galaxy? Satellites. Who said that? Who said that? Huh? Yeah, that's right. Satellite. One can have satellite. The satellite travels all the way from the far off the galaxy and to the close to the galaxy and then come to the orbit. If you take the orbit of the satellite, then it actually is also like now behaves almost like a test particle, provided we have this kind of condition satisfied. The satellite mass should be much smaller. Okay, and then it can go around the galaxy and it will traverse a long distance, even farther than the hydrogen gas. Then we can find out the potential galaxy, much more confidence, the dark matter potential. So coming back to here, so is the Vc equals to constant. So you see the circular velocity remains constant in a typical spiral galaxy. So from there, we can what we deduce from this. What we understand from this, that if you had only the stars, then your circular velocity would fall. If we had the stars and gas, then little bit higher, but still not this much. So to account for this mismatch in the observation and theoretical expectation or the measurement, theoretical measurement, then it seems like there should be some unseen matter. That's the whole idea. So unseen matter should be such that the velocity, circular velocity, due to that is constant. And when Vc equals to constant, so you can think about if you have a spherical distribution of matter, then m within a bar is proportional to r. Correct? So gm over r. So BC square equals to Gm over R. M over R and divided by R should be proportional to, right? And this is possible only when rho is proportional to 1 over R square. The density of the matter is proportional to 1 over R square. Follow? No? Everyone? These are the deduction from here. BC constant. BC is Gm over R. So then M of BC is constant, so this should be proportional to radius. So it should be a spherical distribution of matter in which the mass within a radius is proportional to the radius. So mass increases, radius increases, mass also increases. So then that requires a density, volume density, which is proportional to 1 over R square. Fine? It's a 1 over R square. Then this is also tells you that the potential of that matter, which is the unseen matter, is ln. Do you follow? If you have a potential which is log r, what will be the velocity? You know what is the definition? How to calculate circular velocity from a potential? How do I calculate potential? Sorry, circular velocity given a potential in this system. I come from there clear, right? So what is BC square? Del phi? Del phi by del r. That's all. Del phi by del r what? This is like a force, gradient of the potential. Huh? To be calculated at r naught and plane of the galaxy. Right? So you have a log r potential, you can plug in the log r potential, you will get constant. Clear everyone? Fine. So most spiral galaxies have circular velocity which is almost constant in the far out. So hence the deduction is that it contains an unseen matter, which is a dark matter, and the dark matter should be such that its density is proportional to 1 over r square, potential should be proportional to logarithm of the radius. Simple. If it is like that, then we can think about a potential in such that phi of, let's say, logarithmic potential is BC square by 2 ln of RC square plus x square plus y square by e square. I'll explain this, but you can see that the trouble is that this density distribution is that when r goes to 0, this density goes to infinity. Right? When r goes to 0, this density profile is not a nullity, so it goes to infinity. Also, the trouble is that as we integrate, m of r is a mass within radius. As we move at the radius, it is more and more mass. So if we integrate over 0 to infinity, the total mass will be infinity. Right? So a simple solution from this gives you an unphysical solution. Isn't it? So a simple solution from this, we come down to this, and we get a dark matter whose density distribution becomes like blow off at the center. This is very, very like the high density, and its total mass is also becoming infinite. It can't be a physical solution. Very interestingly, we will not have time to go through this, but if you take, for example, just Maxwell Boltzmann distribution. Okay, it's e to the power, let's say, v square by 2 sigma square tau. Velocity distribution of the stars. V square by 2 sigma square. In that, I can think about e to the power minus e by sigma square. Right? E is the energy. If we consider the energy is half v square, this is the part we have not done. Because what is considered is the kinetic energy, this is the ideal gas. I can think about that the gas is in a potential. So it can add a potential term. So it's a total energy, so it's e to the power minus e over sigma square. Right? So there will be the constant term here. Right? You will integrate to normalize this part. And then you can just say that, okay, I want to know, this is the energy distribution of the particles. What is the density distribution? Right? So if this is F of V like this, then your density distribution rho is generally F B3V. Okay. So if we do this process and at the end use, for example, a spherical distribution, on this we calculate rho, and then from rho you can calculate the use of the Poisson equation of the potential, and you can calculate the potential from this. Importantly, what I want to say that get density, which is at the end the solution for this would be also 1 square. You can do this while you are here. If you have a difficult day, follow consider the distribution function of the particles like this, which is the Maxwellian distribution. From here, you calculate integrate over the velocity space. You get the density distribution. From the density distribution, it will depend on the phi. Right? Density distribution will be depending on the phi because e to the power minus phi will come out, right, of the integral, right? And then you can use the Poisson equation to connect. That square phi equals 4 by 0, the rho will come here, so you get an equation for a potential. On one side it will be e to the power minus phi divided by sigma square, some other term here, and then we will have the differential of the phi on the left side. Okay, then we can calculate the potential, solution for the potential. Once you solution for the potential, plug in it here, and you can calculate the density distribution. That density distribution, since I don't have, happen to be also like 1 over r square. So this is called the singular isothermal solution for dark matter. This is a singular isothermal sphere. Why singular? Because 1 over r equals to 0. The singular isothermal sphere. Okay. So to normalize that, one does add some kind of so that it does not go to infinity at the center. So if I plot this r versus rho, it will be like this. But we don't want at the center. We want to like something like nice. Okay. This is what not desirable. So what we can do is a rho proportional to 1 over r square. So you can think about the rho naught divided by r square. Yes, rho naught divided by 1 rc square plus r square. I add a term which is called some kind of a constant scale factor such that when r equals to 0, it does not go to infinity, but it goes to some kind of constant value. Okay, so this is how you modify the density distribution of the dark matter halo, and this is basically called pseudo isothermal pseudo isothermal halo. For that, this is the observed model of the dark matter halo. Okay, you can't use 1 over r square just. You have to use rho into this r square plus r square. For the same thing, I also added here. Log of r square, I added co-radius, and I have added an ellipsoidal coordinate x square plus y square q square. Q is like flattening of the. It's not a circle. Could do that also. Q is equal to 1 with the circle. X square plus y square is r square. So in the q is equal to 1 is a circle. But q is equal to like less than 1 is an object. So there is a configuration. We do not know what is the dark matter halo is. So this is what basically is. Is from here this part is it clear? Is there any question? Because Ajit will come and ask you so.
And by integrating of r from 0 to instead of integrating from 0 to infinity,
But what did you do at the center?
then this density.
No.
Why should it?
Because the m is proportional to r. Yes, r. So r equals to 0 is nothing. So it's basically a solution which is basically goes like this. M of r proportional to r. So it means you cannot just block this part. Even if you block this part, there will be infinite mass, isn't it? And the density structure is also not a physical solution at the. You can't avoid this center just like this. This is coming from a very simple deduction. It's analytic, no approximation, nothing. And then this is what I said. It is even more rigorous. You can do it even more rigorous. This is where I gave a very simple argument based on observation. This is where you start with the theoretical thing and you derive this thing. You get an unphysical solution. Okay? So this is, I think this is not avoidable easily. But the way we do it, basically we do tricks. The tricks is to basically add some kind of a over here and I say, okay, at least I state the solution. There are lots of these techniques are there whenever there is a singularity, how to handle the singularity. So there is a various ways to that, But so very quickly I will go. So let's think about. Let's go back to the orbital bit again. So now I'm thinking is that I have a radius r and I have a co-radius r. If and I said that we are talking about the orbit, which is as you go in the very far away in the galaxy from the center, you have basically this kind of orbit, loop orbits. We want to know what happens at the center, close to the center. What is the center here? Which means that when r is less than rc, rc is some kind of co-radius, right? When r is less than rc. When r is less than rc, phi n can be expanded also. So can you find out what happens when this is less than rc? Consider this as r is less than rc. What happens to the potential? No clue. Is the question clear?
Just the small part will come up when you take the expand.
You will expand this?
Yes.
How do you expand?
You ln1 plus x is
Yes.
plus
ln1 plus x kind of.
x.
What is that? What do you get there? X. First term? Huh?
Yeah, I think x.
Yeah. So it's a VC square by 2 x. What is there? X, then the second order term, right? No, the x is basically this. X square plus y square by q square. No? So I can think about this as r VC square into x square plus r VC square by q square into y square. So when r is less than rc, which means we are very deep inside the core, very close to the center, now the potential is already regularized. So then the phi L becomes a half into bc square into x square. So we can write this as a half into, let's say, omega x square into x square plus half into omega y square into y square. Exactly like your Issa's figure. This is again two-dimensional oscillator with a frequency x direction omega x, y direction omega y. So then I have a plane here, which is a y and an x. So I am bounded by the omega x direction, right? So this will be energy on this side, and there will be energy on this side. So then I have approximately, I have a space of the phase space of the orbit will be like close. So anytime it starts from any direction, it will go like this. It will fill up this. Right? If omega x and omega y are not, again, this case is an incommensurate. If they are integer, ratio of them are integer, you will get after few turns they will get. Okay, so these orbits are called the box orbits, and there is a lot of box orbits here. So these are the typical the box orbits. This is done in x dot versus x, which is the phase space. X dot is the x dot velocity, and the y the x direction. You see, these are bounded. Then, if I change the energy of the orbit, it becomes a little bit pinched, but all that right now there. Okay, box orbits are very important because so in the center of the galaxy, when this condition is satisfied, which is often the case, under this approach, very general approximation without doing much, right? So you know the basic nature of orbits of the stars in the galaxy at the center, the box orbits, right? These are box orbits, and outside there are loop orbits. So there are many twists that the spinning can happen depending on the energy. Every time you calculate the energy, so an orbit is often or always have to have an integral of motion to be first determine the energy, the angular momentum, and that will tell you what will be the orbit. Okay. So in this case, in general, you would expect this part. What is the significance of this? You see, unlike the loop orbits, which do not go through the center, the box orbit can go through the center. Box orbit can go arbitrarily close to the center. Right? So this is a very important implication on that, because so you are talking about very close to the galaxy, center of the galaxy. The center of the galaxy also have something with supermassive black hole. Most galaxies have supermassive black hole. Supermassive black hole have what is called as a Schwarzschild radius, which is 2gm by c square, and it also has another important quantity, which is called the sphere of influence, which is 2g mbh divided by sigma square. Sigma is the velocity dispersion of the stars. Sigma is the velocity dispersion of the stars in the center of the galaxy. So this is not by c square, but it's a sigma square. So sphere of influence is large. Schwarzschild radius is very small. This is you divide by c square. Okay. What happens is that moment the supermassive black hole is the center of the galaxy, and it has a, let's say, sphere of influence like that, and any of the stars which will go close to the sphere of influence will get absorbed. Will get absorbed. So the box orbits are feeders to the black hole. If you see like the stars plunging into the supermassive black hole, it is due to its box orbit nature. If the orbit goes like this, then it has to lose angular momentum and then close the cups to become. Okay, so if you have a many more number of box orbits, that can also actually feed the black hole much more efficiently. So these are the nature of the orbits. So whether galaxy like to have those orbits or not, that's like different question. Okay. I think I should stop, and if there is anything you ask, do not go please. Any other question?
So how the component issue is actually calculated for sun?
Kappa over omega. Yes. So there is something called say the full times. People have to know whether the Milky Way galaxy, the stars are what kind of rotation, whether they rotate, and what kind of rotation they are. Okay, so they what they were determining is that from the sun they go around in azimuth and determine the velocities of the stars. Okay, so the radial velocity or the line of sight velocity of the stars. So line of sight velocity of the star they calculate as a function of phi, and they found from there one can do a little bit of like dynamics and or something called the Wood constant, which is a measurable quantity. Okay, so the measurement of the Wood constant you can read that using that one can directly get an estimate of the kappa over omega index. If you have any further question with that, you can ask me later. But this is the key is the Wood constant measurement. Young Wood. Young Wood. Dutch astronomer. Wood constant A and B. Using that one can actually determine. Okay. Any other question? For RC. RC you don't determine, it's a model. So you have a rotation curve, data, and you want to fit your data, you have a model. So basically do a chi-square. Then get the velocity from this, and then you have the observed velocity, and using that you can do the chi-square minimization, and then you get this as a parameter, this and this as a parameter. So you get the parameters. Anything else?
Online participant, if you have any doubts or questions, please raise your hands.
All right. No question. Fine. Thanks.
There's T now. How to pick up the T and push it about 5. Bring the T. Okay. I know that. Yeah, exactly. I thought I was just स्क्रीन खाली कर दो।